Good afternoon. This is a thin film deposition lab. Basically, we deposit thin films of superconductors and to study its properties. So, making it into thin film is important. And when I talk about thin film, it is a nanometer scale. Let's say around 2-3 nanometers all the way to 500 nanometers would be the range that we are working in, but mostly around 15 nanometer. So, one of the first process that we use to make a thin film is the simplest system called as the evaporation. In this evaporator, it is like a normal bulb where we have this tungsten filament coil which is in vacuum there. So this is like a huge bulb and we have a coil quite inside here. This is one of the coils, tungsten filament coil, and we put a silver piece inside it, and the substrate or the sample is deposited, is kept upside down with a clip, and then we will generate a vacuum here, and once we get the good vacuum around -6 range or -5 range, we will then give supply to the tungsten. The tungsten will heat up and the silver will evaporate and deposit on as a thin film onto the base or the substrate that we use. So most of the substrate that we use are either silicon or glass, or it can be MgO, some substrate which is much thicker compared to the thin film. So this is one of the simplest process to deposit a thin film. So here normally we can use single element like silver or gold or lead, which can easily melt and evaporate. Beyond this, we have another system that is sputtering. Now in this system, what we have is that we sputter the ions. So we create a vacuum in the chamber, and the material that we want to deposit is bombarded with argon ions. So this whole chamber is evacuated and we put in argon gas, and with supply given as a negative potential to the element that we want to deposit, we will bombard the argon ions onto it, and a plasma is created, and this material will get on deposit onto the base substrate, and that's the thin film that we deposit. So here we normally grow niobium nitrides, superconducting thin film, so it can be niobium. When I say niobium nitrates, now nitrogen also comes as a role along with niobium. Niobium is a superconductor which is 9 Kelvin, but if I want niobium nitrate, I have to add nitrogen gas in the system, which will react with Nb, and then the Tc or the superconducting temperature goes to 16 Kelvin. So the process, other than argon, we will add nitrogen, it will be reactive Tc magnetron sputtering. This is another system to make thin film. The third one is a PLD. In both the system that we saw, the evaporation as well as sputtering, the whole thing is inside. The element as well as the substrate is inside. Here we have a laser, so which is a UV laser, 248 nanometer wavelength, which is up there on the other end, and then we have an optic system, and through which it will come inside the chamber. The UV range laser will come and hit the target or the material that we want to deposit, and it will hit on it, and then the material that will come out or the ablated material is deposited on the opposite side. So here normally we can use complex materials, like in the initial days the laser PLD became a boom because of yttrium, barium, copper oxide, which could be easily deposited by PLD. So all this material could be easily be absorbed and it could ablate, and the same stoichiometry as the superconducting material, base material, could be got onto the substrate. So the oxygen was added to the system in the vacuum, and the yttrium, barium, copper oxide thin films were got in, and this the Tc was around 90 Kelvin. So here right now we are working on lower TCs, which is MOGE, molybdenum germanium thin films. So that's the basic 3 thin film deposition systems. And to look at the thin film deposition films, if the superconductor is good or not, there are 2 ways. One is do a four-probe measurement. That means you pass current and look at the voltage and see at what temperature the material becomes superconducting. So that is a four-probe measurement, and we will put this sample and cool the system, and then looking at the temperature and the resistance, we can see the graph. At some particular point the resistance will go down to complete zero, that is the Tc point. So that's one method. Second method is in superconducting, once the material becomes superconducting, it can repel magnetic field, the Meissner effect. So we have 2 measurement systems, which will just show you, which were used for measuring these 2 characteristics of the superconductor. So here we have a liquid helium double wall tube that goes into a system here, and this is a 4-probe measurement system. We can either do 4-probe or 2-coil system. In 4-probe, what we do, this is the temperature controller, this is the current and the voltage source, and here is the coil setup. Okay, now the coil, I'll just explain that a bit. These are all inserts that we use in which samples can be put in. I'll just want to open it. So here, in the two coil setup, the sample is sort of sandwiched between two coils, primary and secondary. So there is always a magnetic field there. As long as the material is beyond superconductivity, the signal is passing through. The moment the material becomes superconductor, it will block the magnetic field. Then we know that's the point in which the TCS comes in. So this is two coil or AC susceptibility measurement setup. Whereas in the RT measurement, we have 4 contact wires, 2 current and 2 voltage poles. I'll just show you one sample which we use for RT measurements. Okay. So normally for 2 coil, this is just the sample and there's no soldering or nothing is done on the sample. So this sample can always be used for many other tests later on in the 2 coil setup. In the 4 probe, I'll just show you the sample. So in the 4 probe setup, I said there will be 2 current and 2 voltage leads. So extreme 2 are the currents and here is the voltage leads. So these 4 wires will go into the system and then we'll cool the system, and then we can look at the current that is passed and the voltage, and we look at the resistance, and the graph can be plotted, resistance on the y-axis and the temperature on the x-axis, and then we can see the TC coming down, resistance coming down at a particular temperature. So that's the basic setup here. Thanks.